So the talk is in two parts. We're going to look at inlining first. We'll talk about what inlining is in general, and then we'll look more specifically at inlining on the JVM and how you do it in Scala. And then finally, we'll look at some benchmarks to see whether it's worth doing and what kind of effect it has on the performance of your code. And then the second half of the talk is specialization, which I spell quite inconsistently, so apologies for that. Before we look at specialization itself, we'll look at a bit of background, like what the problem is that specialization solves. Then we'll look at how it works in Scala, and again, we'll look at a few benchmarks. On the right-hand side, there is a warning. There is bytecode in this presentation. It's the final session of the day. Your brains are fried. You just want to go and drink free beer at the party. So let's all sit in a big dark room and stare at bytecode. Just quick self-introduction. I'm Chris Birchall. I work at The Guardian in London, which is a newspaper and also a very popular online news resource. We use Scala very heavily at The Guardian, for everything from the front end to the back end APIs to the in-house CMS that we've built. All of our monitoring tools, pretty much everything is in Scala. We were a very early adopter of Scala. We've been using it for years. Also, my book is out recently, so nothing to do with Scala, but please buy it anyway. So, one question you should ask before you agree to listen to me for the next 45 minutes is, why should you care? Why is it worth learning about these things? Inline and specialization and performance and optimization and so on. And the answer is that performance matters sometimes. So, I come from a Java background, and back in the bad old days when I was writing Java, I was thinking about performance pretty much all the time. It was quite a high priority. Like every time you wrote a bit of code, in the back of your mind, you'd be thinking, how is this performing? Am I using the right data structure, or am I looping in the correct way, and so on. But then, when I moved to Scala, I went through a kind of honeymoon period where everything was suddenly immutable and functional, and I had these nice primitives like map and filter, and suddenly elegance became the top priority, and performance was not that important. And I think in a lot of cases this is valid. This is totally fine. Unless you have real performance requirements, or your application is really struggling to perform to users' expectations, then fine, don't worry about performance. Don't prematurely optimize. But occasionally there are times when you need to worry about these things. And in those cases, you need to know how your Scala code is actually compiled into bytecode, how it's running on the CPU, and what kind of optimizations you can use to make it perform better. So without further ado, let's have a look at inlining. So what is inlining? Basically, it is removing a function call from your program by copying the function's body into all of the places where the function is called. So I have a quick example here. We've got a target function. This is the thing that we want to inline. And then we have another function that is calling it. And then after inlining, you can see that the function call has disappeared, and the body of the inlined function has been copied into the call site, with obviously the A and B being turned into X and Y. I mean, just for the sake of the example, I've shown the inlining happening to your source code, like Scala source being transformed into other Scala source, but of course this is not what actually happens. Your source code is what you write on the left-hand side, and the inlining happens at the level of JVM bytecode, or possibly at the level of assembly. So this is inlining. Why would you want to do that? Why is this good for your code? There's a couple of reasons, which we'll look at in detail in a second. One is that it removes the overhead of making the function call. Every time you call a function, there is a certain overhead cost associated with that, and if you can get rid of the function call, then your program will run faster. So functions are bad, remember that. And the second and probably more important reason is that it's an enabler for other more powerful optimizations to take place. Compilers or optimizers are quite good at optimizing within one function, but then as soon as you start crossing the function boundary, you try and compile across the whole program, across multiple functions, optimize across multiple functions, it becomes very difficult or even near impossible. So if you can get rid of that function boundary so that all of your code is now within the confines of one function, then it becomes easier to optimize. And it's worth pointing out that inlining is a kind of a classic optimization. It's been around since the Stone Age. It's not related to the JVM or Scala in particular. It's been done since C, I guess. So here's our first bit of bytecode. We have the same sample that we had just now. We've got our target function and our caller function. And on the bottom left-hand side, you can see the bytecode for those functions. I won't go into them in massive detail, but you can see that after inlining, there's a lot less bytecode for a start, so that's a good thing. There's less stuff to execute. And most importantly, the thing circled in red, the invoke virtual, has disappeared. Now, this invoke virtual is the bytecode used to call a virtual function. Depending on what kind of function you're calling, it'll be either invoke special or invoke virtual. And getting rid of this means that we've got rid of a lot of overhead. So if we have a look at the JVM spec for invoke virtual, we can see exactly why it's bad and we want to get rid of it. So the three things circled in red are what the JVM needs to do when it invokes a virtual function. So the first one is lookup. It needs to find the function because it may not be defined on the concrete class that you're actually dealing with. It might be higher up the type hierarchy. So it needs to find it. Then it says a new frame is created on the Java virtual machine stack. So this is like stack being allocated, memory being allocated. So that's obviously going to have a cost associated. And then finally, it says the Java virtual machine PC is set. And PC is program counter. And what this means is that your program is doing a jump. And a jump is kryptonite for CPUs. The one thing that your CPU wants to believe about your program is that whatever it's doing now, it will continue to do in the future. So if you're executing this instruction, and then this instruction, and then this instruction, the CPU thinks, I spot a pattern here, and it starts to pre-cache the next few instructions. It assumes that you'll keep doing this, but then suddenly, bang, you jump over here, and it hasn't cached any of these things. So it needs to suddenly fetch those from main memory and start executing over here. So that's quite expensive. And the other benefit of inlining that I mentioned is that it enables other optimizations to take place. So just an example here. On the left-hand side, we have a class A with a field X and a method +1. And then we have some function which calls this. It instantiates a new A with X set to 1 and calls +1 on it. So step 1, inlining. You can get rid of the function call to +1. Just replace it with X +1. And then as soon as you've done that, Hotspot's escape analysis can kick in, realize that you didn't even need to allocate a new A. You can just reduce the whole thing down to 1 + 1, which is obviously trivial. And I guess Hotspot would also realize that 1 + 1 is equal to 2, so it would probably optimize even further. So based on all of that, it looks like inlining is a good thing, and we should do lots of it. So the obvious question is, why not inline everything? Why don't we just inline our whole program into one huge function, and then we could optimize it as like crazy, and everyone's a winner. So the answer why we don't want to do that is that code is data. And the less cryptic answer is that every time you inline a function into multiple call sites, that's duplication of code. So the more inlining you do, the bigger your code gets. And if it gets too big, then the working set of your code, the hot parts of your code, no longer fit into CPU caches. And as soon as you overflow from the cache, as soon as you bust the cache, then your performance will radically decrease. So it's a trade-off. You want to inline as much as you can, but you don't want to push things too far because then you run out of cache. So we only want to inline hot functions, meaning functions that are called very often in your code, like really important stuff. And ideally, we want to inline the smaller, hotter functions, because then more of them will fit without overflowing the cache. And it turns out that Hotspot is pretty good at this. I mean, that's the whole point of Hotspot. That's what it was designed for. Hotspot is a JIT compiler, a just-in-time compiler, that measures how many times every function in your code is called when your program is running. So it gathers metrics about your code. It discovers these so-called hotspots, these things that are called really heavily. They're the most critical paths in your code. And then it compiles them to assembly and then optimizes them aggressively. That's the point of Hotspot. And the reason it's so good is that it has access to this runtime information, this metrics about how often things are being called. Obviously, if you were to do inlining in the compiler, then you don't have access to that information. You don't know what's going to be the most important part of the code base. So Hotspot uses various heuristics to work out what it should be inlining. It's got some quite complicated conditions, but in general, it tries to inline things that are small and things that are hot, and it tries to avoid making the call site too big. If you inline a function into another function and that caller ends up becoming huge, then that's not good, because you have this problem of the caller function not fitting into the cache anymore. And then it has a few other conditions, like it can't inline native methods and so on. As you can see, you can tune all of these heuristics quite heavily if you want to. You can set these JVM arguments to decide how you want to inline things, but the defaults are pretty good for most use cases. And if, like me, you're interested in this stuff and you like to spend your spare time looking at bytecode and x86 assembly, then I really recommend this tool. It's called JITwatch. It parses the logs that you can get Hotspot to output with various JVM arguments, and it shows you exactly what the JIT compiler has done to your code. So after every iteration of the compiler, you can see how it's changed your code versus the previous iteration, where it's optimized and which functions it's inlined and so on. So this is Scala days, but so far I haven't really talked about Scala. So this is how you do inlining in Scala. Until now, I was just showing you how things might happen in Hotspot at runtime. But if you, instead of doing that, or as well as doing that, you can also inline things at compile time using the Scala compiler. So you can add these annotations at inline and at no inline, and it's pretty obvious what those mean. So the at inline annotation says, please inline me, and the other one says, please don't inline me under any circumstances. But just doing that is not enough. If you don't enable the -optimize flag, then the compiler will not do any optimization. So that includes inlining. So it will ignore these annotations. So don't forget to do -optimize. And it's also worth adding this other option called -y inline warnings. And if you add that, then it will give you a compiler warning if it wasn't able to inline for whatever reason. So if you annotated your method with @inline, but it couldn't inline it because it wasn't final or whatever, then it will tell you about that. A word of warning about -optimize. It is quite buggy, apparently. The Akka docs, for example, have a big red warning box that says, do not use -optimize. So use at your own risk. So you might think that you just add these @inline and @noinline annotations, and it will inline them or not inline them for you, according to that. But it's actually a little bit smarter than that. So Scala C has certain heuristics that it uses to decide which methods to inline. So first of all, it will only inline so-called effectively final methods. So this means basically a method that can't be overridden. It's either marked as final, or if it's inside a class that's marked as final, or whatever. Like, the compiler knows that at runtime, this is definitely the method that will be called. It won't be overridden. Then it treats code differently depending on whether it's your own code that's being compiled as part of the current compilation run, or it's somebody else's code, for example, an external library that's already been compiled. So for external libraries or already compiled code, then in general, it'll only inline things that have been annotated with inline, but it has special rules for certain bits of the Scala library and higher order functions and the so-called monadic methods. So the monadic methods are map, flat map, filter, and one more, I think. And there's actually there's an if statement somewhere in the compiler that says, if the method is called map, or it's called flat map, or it's called filter, then do something special with it. So when it decides whether to inline a method or not, assuming that it can inline it, if it's been annotated with @inline, then it will inline it. It'll respect your wishes. But if it hasn't, then it will calculate a score to decide whether it's worth inlining or not. And it's based on these heuristics. So if the call site, the caller method is small, then don't make it too big. Don't inline methods that are themselves already quite big. Do inline higher order functions, and so on. So this is how Scala works right now. This was all added in Scala 2.10.0, and it still works basically like this. But in 2.12, there is a brand new backend called GenB code, and that includes a new optimizer. So all of the inlining code has been rewritten from scratch. And the idea when they rewrote the inliner was to simplify it a lot and try and make it a bit more deterministic, so you can tell more easily whether a certain function is going to be inlined or not. So they tried to distill it down to just one simple rule that says only inline marked methods, and always inline them, including under separate compilation. So that was the idea, but then later on they actually added a few more rules. They decided to also inline higher order functions. And the reason for this is to fix the so-called inlining problem, which is outlined quite nicely in a blog post by Cliff Click of Azul. I won't go into the details of that, but it turns out that inlining higher order functions is quite important. If you don't do that at compile time, then Hotspot will really struggle to do its inlining. So it's all about helping Hotspot out here. So the point of the new optimizer, I guess, the overall goal is to have better synergy with Hotspot. Don't try and do the job that Hotspot is already good at doing anyway, but do kind of help it out where it needs some help. Okay, so we're going to have a look at some benchmarks now to try and see what kind of effect adding these annotations has on our code. Just a word of warning that this is probably all wrong. So when you write benchmarks, there's a few different ways you can do it. You can write a very specific micro benchmark that just looks at whether changing this one line of code will change the performance of this tiny little operation from 1 microsecond to 1.1 microsecond. But I prefer to do a kind of more real-world-y benchmark where I try and simulate code that you would maybe write in a real-world program, and somewhere inside that code, you change one line and see what the effect is on the runtime of the overall operation. So to that end, I came up with implementing a fast Fourier transform. This is not something that we use at The Guardian very much. You don't really need to do a fast Fourier of the news. But I don't know, it is used quite a lot in other domains. I mean, it's used in MP3 encoding and all kinds of things. I implemented the Cooley-Turkey algorithm because it has a really good name. Again, I won't go into the details, but it's a recursive algorithm. It lends itself quite nicely to a kind of functional, immutable implementation in Scala. And the meat of the algorithm is just loads and loads of numerical operations on complex numbers. So I modeled a complex number as a case class, and it's got plus, minus, and multiply methods. And the point of the benchmark is, if you annotate these with inline or no inline, what happens? So the moment of truth, let's look at some numbers. There's quite a lot going on this slide, but I'd like to draw your attention to 3 things in particular. So first of all, can you see my mouse here? If you just have a look at the difference between this left-hand column and this right-hand column, the left-hand side is what happens if you just disable inlining completely in hotspot. And then the right-hand side is normal operation, where you don't pass any weird JVM arguments, you're just running Java normally. And you can see that disabling inlining makes the code 3 or 4 times slower. So obviously, hotspot is doing quite a good job. Next thing to note, if you look at the right-hand column, the top number, 360, is annotating with the inline annotation, and the bottom number is annotating with no inline. And like give or take the error, they're basically the same. And the reason for this is that no matter whether you annotate in Scala or do the inlining in Scala C, hotspot will come along and just inline it for you anyway. So there's no need to worry about it. Just leave it to hotspot. And then the final thing to note, if you compare these numbers here with the ones below, you can see just by upgrading to Scala 2.12, we can look forward to, what's that, about a 10% speed up. So that's quite nice. And this is for a number of reasons. It could be the new optimizer work that they've been doing in Scala 2.12. It could be the use of Java 8, what are they called? SAMs. The re-encoding of lambdas to use Java 8 classes. But anyway, it looks like Scala 2.12, for this use case at least, is faster than 2.11. So that's good news. Further reading, I got a bit carried away here, but there's just so much information available online about inlining in hotspot or the internals of the JVM. So I'll put the slides online and you can read at your leisure. So that's all I have for inlining. Now we'll look at specialization. But first of all, we'll have a look at some background on how types and generics work in the JVM and in Scala. So this is just a bit of a recap. It's probably familiar to most of you. And Dimitri went through this stuff in his talk earlier today, if you were in that. But types in the JVM are split into 2 types of types. There's primitives and reference types. So primitives are Boolean, byte, char, int, and so on. They are not objects, so they're small and memory efficient. There's no object overhead. They're just raw values. And reference types are everything else. So anything that extends from Java lang object. They are stored on the heap whereas primitives can be stored on the stack. And if you want to reference them, then you need to pass a reference to the object, not the object itself. So there's a level of indirection there. If you're working with a primitive, then you have the value right there. You can do what you like with it, but the reference, you have to do a jump from the pointer to the object itself. So how does this play with generics? Unfortunately, not very nicely. So we'll have a look at a generic piece of generic code in Java, and in a second we'll see how that translates to bytecode. So we have a public class generic, which has some function method foo, which is generic. So it says, I take an A, but I don't care what its type is. I'm just going to call it A. There's no no bounds on this at all. It could be anything. It could be a primitive int, or it could be a string, or whatever. And then underneath we have another function test, which is calling this. So first it calls it with a string, which is a reference type, and then it calls it with an integer, which is a primitive. So let's see how this translates into bytecode. So first of all, underlined at the top, you can see that even though we haven't said anything about objects or reference types or given any kind of bounds on our function, on its parameter, it says that it will only take a Java lang object, or obviously a subclass of Java lang object. And this is basically because generics is broken in the JVM. It was added retroactively after the whole type system and the bytecodes had been already formalized, so this is the best they could do. And then underneath that, we can see our two invocations of that method. The first one, we are passing in the string hello, and we're passing that in as an object. That's fair enough, because it is an object. It's a reference type. But then the second function call, we have a primitive, but that doesn't extend from Java lang object, so we need to convert it into a reference type. We need to convert it into an integer with a big I before we can pass it into the method. So can anyone tell me what we call this process of converting from a primitive to a reference type? That's right, boxing. So boxing is something we want to avoid for various reasons. Well, firstly, it's just it's wasted effort, really. Like, we already have the value. Why do we need to convert it to another representation of the number? It's wasted CPU. But also, it involves an allocation on the heap. So every time you do this boxing, you convert an int to an integer. You're allocating a new object on the heap, and that will have to be garbage collected, so you're increasing your CPU usage in that way as well. And yeah, you're increasing memory pressure. So we'd like to avoid that. So much for Java. Let's see how it works in Scala. So this is the root of the Scala type hierarchy. We have an any at the top, and extending that, we have any val and any ref. So any val represents the primitives, the value types. So we have int and double and so on. And they are encoded on the JVM as primitive types. And then on the other side, we have any ref, which is pretty much equivalent to Java lang objects. So this is the reference types. So we have the same kind of thing that we had in Java. So let's see generic code in Scala and see how that maps to bytecode. So here I'm using the standard library mutable map. I create a new map with an integer type for its value type. And then I call put on it, and I pass in a primitive 1, 2, 3. So if we look at the bytecode for that, you can see that we have the same problem. Before we can call the function, we have to convert from an int, a primitive int, to a reference type, an integer. And can anyone remind me what this conversion is called? Boxing. Very good. OK, so the point of specialization is to avoid this problem, to work around this problem. And it does this by generating multiple versions of a class. It generates a different version for each primitive type, and then the compiler will choose the correct version, and it will call it directly, so you don't have to go through this boxing process. So you use it like this. It's pretty simple. You just you add the specialized annotation to your type parameter. So I've got a my special map here with a specialized type parameter A. And when I compile this, the compiler will generate all of these 10 different versions of my class. So there's one for each of the primitive types, there's one for null, and there's one for any ref. So just the normal non-specialized version. And then if I want to use this my special map from some other piece of code, I can do it like this. So my foo method here doesn't need to know anything about the specialization. It doesn't know that my special map is specialized. It just calls it with type parameter int. And then it puts 1, 2, 3 as its value. So we'll see how this looks in bytecode. You can see everything is now green circles instead of red circles, so that's a good sign. The top line, the first line, you can see that it's instantiating an instance of not my special map, but the specialized integer version of my special map. And then the second green circle, it has a capital I, which means that it's passing in a primitive integer. So there's no boxing going on here. Everybody's happy. One thing that I didn't understand for quite a while is how does the caller, how does the client code know that your my special map is actually specialized? Say if I want to release my special map as a library and I put it in a jar, stick it on Maven Central, and then somebody wants to use it, how does the compiler know that it's actually specialized? And the answer is that specialized is a so-called static annotation, which means that it gets persisted into the Scala signature, which itself in turn is persisted as an annotation inside the class file. So somewhere inside that big blob of bytes, if you decode that, you can see the specialized annotation in there. So when the compiler sees that, it knows that it's specialized, and it will automatically choose the correct specialized version of that class when it needs to. So once again, just like inlining, we have a trade-off here. Specialization, similar to inlining, it generates a lot of duplicated code, even more so, I guess. So if you have one type parameter, like we had for my special map, then it could generate 10 types. But if you have 2 type parameters, it could be 100 types. 100 classes, and so on. So it's 10 to the n, where n is the number of type parameters that you want to specialize. That could be a huge number of classes. One thing that you can do is to specify the types that you want to specialize on. So here I've said that I only want to generate specialized versions for int and long and double. So then there'll only be 4 classes, I guess: int, long, double, and any ref. But like Dimitri said in his presentation earlier today, this is it's not that helpful, because say if I'm a library author and I want to release my special map to the world, how do I know what types people will want to use it for? I just have to make a guess. And you can see this problem quite a lot in the Scala standard library. So it's a bit of a mess, to be honest. Tuple 1 is specialized in int, long, and double. Tuple 2 is specialized in both of its arguments in int, long, double, char, and boolean. Tuple 3 doesn't have specialization at all, so there's boxing there. If you're in the front row, you might be able to see a little tiny Muhammad Ali there. He's representing the boxing. Option is boxing. Function 0, 1, and 2 are just random combinations of specialized, different types of specialized. Function 3 or more doesn't have any specialization. And most of the immutable and mutable collections also no specialization. So if you do want to use specialized collections, there are some alternatives. If you can't really use the standard library, but you can use, for example, dbox. This is written by Eric Osheim, who's the creator of Cats and Spire and various other things. It's quite a nice mutable collections library that uses specialization. Then there's Metal, which is a fork of that project, I think. And also worth mentioning is miniboxing. So this is a kind of the second iteration of specialization, I guess. It's a version 2. It does basically the same thing as specialization, but the implementation details are quite different. It involves using a compiler plugin. You annotate things with mini-boxed rather than specialized. It gives you approximately the same speed-ups or optimizations that you get from specialized, but it doesn't generate as many types of, as many classes, so you have less code duplication. So let's have a look at another benchmark. And the same warnings apply. This is all probably wrong. Again, I wanted to do a kind of real-worldy benchmark, or something a bit more interesting than just a boring old map. So I implemented a Bloom filter. A Bloom filter is a probabilistic data structure that can tell you whether a certain element is probably a member of a set. So you add values to it. You say this element is in the set, this element is in the set, and then later on you can query saying, is this element in the set? And it will either say probably yes or definitely not. So depending on your use cases, this can be quite useful. And it's a lot smaller than just a normal set, so it's more memory efficient. So I implemented a Bloom filter class, which has a specialized type parameter, which I specialized in int. It also needs some hash functions, so that, well, for various implementation reasons. So that's also specialized in int. That's a type class. So let's look at some numbers. So the operation here is to insert one number and then query for another number, say. And as you can see, adding specialization doesn't really appear to make much difference to the performance. But to be fair, I think this is a problem of the benchmark rather than specialization itself. Specialization, like in the short term, at the time you actually call the function, the only overhead that you're going to save is one boxing, one call to that boxing function. So that's not much of a speed up, to be honest, getting rid of one function call. But over the long term, if you're calling this over and over again, then you're allocating more and more objects onto the heap due to all of this boxing going on. So you're exerting memory pressure, and eventually GC will kick in and your program will slow down in that way. So I don't think that this benchmark really takes that into account, or it doesn't show up in these numbers, that kind of long-term memory pressure issue. That's quite hard to benchmark, I think. Also, another thing that specialization can give you, another benefit, is that depending on your use case, you might have an array, a very large array of values inside your data structure, and you might want to iterate over them iterate from start to finish. And in that case, it's much better if it can be a primitive array rather than an array of references to boxed objects. Because if it's a primitive array, then you get the benefit of spatial locality. You get all of your values nicely in contiguous memory. So that can be another big benefit of specialization. But in this case, in the Bloom filter case, we don't do that. So obviously that wouldn't show up in this benchmark. So yeah, slightly disappointing result here, but I think it's the fault of the benchmark more than anything else. So a bit more further reading here, and also, I haven't listed it here, but Dimitri's talk from earlier today was really interesting. He was talking about automatic specialization that he's adding to the Dotti linker. So one day in the bright future, we'll not need to worry about any of this stuff, and the Dotti linker will just do it for us. Finally, honourable mentions. So this is just a few of the other annotations that I found in the Scala standard library while I was writing this talk and decided not to make a talk about. So you may or may not already know about these, but I thought they were quite interesting. So strict FP annotation. This adds a strict FP flag to the class file, meaning strict floating point. So this is about whether you want your floating point calculations to be as accurate as they possibly can be, or to be consistent across platforms, across any platform that your code might run on. So that's quite interesting. Switch is something that you can add to a pattern match. When a pattern match that you've written in your Scala code gets compiled down to bytecode, depending on what you're doing in your pattern match, how complex the match is and what types you're matching on, it can generate a lot of different types of bytecode, and some of those are more performant than others. So this is an annotation to say, please give me a warning if I've generated bytecode that doesn't perform very well. And finally, elidable is the really weird one. This is an annotation for methods whose bodies may be excluded from compiler-generated bytecode. So if you annotate your method with this, you're basically saying that the method is optional. Like, you don't care if it gets compiled or not. You annotate it with elidable, and then if you pass certain flags to Scala C when you compile your code, it will just rip that method out completely and just replace it with like a 0 or some default value. So
no, it makes sense. It's for a certain and stuff like that.
Yeah, okay. It does make sense. I can see why they added it, but we're not going to use it ourselves in most cases. So in summary, inline, should you use it? I guess probably not. Just let hotspot do its thing. The only exception, I guess, is if you're not targeting hotspot. If you're targeting Android, for example, or Scala.js, then I don't know what their performance is like for inlining. Sebastian might know. I think he's out there somewhere. How does inlining work in JS?
Well, come to my talk tomorrow.
Okay, go to Sebastian's talk tomorrow.
Short answer is Scala.js has its own inliner heuristics that are probably better than what you would think by yourself. So
Okay.
it's the same answer, I guess.
Okay, just to repeat what Sebastian said into the mic. Scala.js has its own inliner and its own heuristics. So, yeah. So, specialized, should you use it? I guess so. In certain circumstances, I think it does make a difference, but unfortunately not in my benchmark. So that's all I have. Thank you very much.